Yeah, so good morning everybody and welcome to the second day of our winter school. My name is Peter Schmelcher. I'm from the University of Hamburg back in Germany, and specifically from the University of Hamburg Center for Optical Quantum Technologies. And this is the building. It's a 2 years old building. It is called a center, not a normal institute. And that just means there are some differences. First of all, there is experiment and theory in the same building. But in particular also we have a small workshop program, we have a guest program within this center. Now, the title of my overall presentations is Rydberg atoms and molecules in external fields. Now, essentially everything we're doing in the ultra-code regime is taking place in external fields, so one has to be a little more focused. And these are the three items I will be covering. I will be first talking about magnetized Rydberg atoms. This is, quotation marks, old stuff, roughly 20 years old, but has a lot of beautiful physics in it, yeah? And you will see it touches upon different fields of physics, and therefore it's really valuable to go back to that one to understand what is happening if there is magnetic fields for Rydberg atoms that are non-perturbatively influencing the system. So it becomes a non-integrable system, and the dynamics is interesting, and the counterpart and the link to chaos and quantum chaos is interesting, and the links to what you call semi-classical physics of non-integrable systems. We will cover that one, and then depending on time I will talk about magnetic trapping. Then there's a second part, exotic Rydberg species in fields. That means we are addressing systems that usually you don't get if you have low excitations and you have weak fields, but you have a strong field impact combination maybe of electric and magnetic fields, and then you get so-called giant dipole states, but you get also for non-neutral systems like anions, negatively charged systems, you get weakly bound anionic species induced by magnetic fields. So these are exotic species we will be covering in the second part. And then in the third part, which is really up to date, this is ultra-long-range Rydberg molecules reminiscent of these trilobite type states and other kind of states which are linking to long-range, very large, weakly bound molecular systems. Okay, so let me start with the magnetic field Rydberg physics. So this is essentially our program for today, at least for today, maybe a little more also of the next session. So I will give you a quite lengthy introduction motivation. Why magnetic fields and why magnetic fields in combination with Rydberg systems, yeah? And then we will go step by step through these three items, which are not of equal length. Some of them are a little longer, like the quantum physics part and the classical dynamics. So first, I will explain you how magnetic fields act on Rydberg systems. If you consider the system to be this classic dynamical system, then it is a non-integrable one. That means you will have chaos. And that links back, since you're in a highly excited system, you're in a Rydberg system, this classical behavior is closely linked to the quantum behavior. So we will bring the two together. And finally, this is the description which you use in order to have a deep understanding of these highly excited systems. You elaborate on modern semi-classics of non-integrable systems. So we have these three parts and try to see what is the phenomenology in Rydberg atoms in magnetic fields, magnetically addressed Rydberg atoms in related to these three items. And then there's this part, magnetic trapping of ultra-cold Rydberg atoms. So let me start with the introduction motivation. So if you talk about a system being exposed to a strong field, what does that mean? I want to elaborate a little bit on the term strong. Now, let's go through what we have available in terms of magnetic fields. Yeah? We have a huge range of magnetic fields being available. If you start, say, with a few Gauss or a fraction of a Gauss or 10 to the minus 4 Tesla, then this is the Earth's magnetic field, which you sometimes have to screen in ultra-cold experiments. But then if you go to much larger orders of magnitude, say you take 10,000 times stronger fields, you end up with something with the strongest possible permanent iron magnets, pocket magnets. Yeah? 0.1 Tesla maybe, and then you have strong permanent iron magnets, say less than 1 Tesla. If you go to the strongest homogeneous magnetic fields available in the laboratory, like for example at the National High Magnetic Field Laboratory in Florida, resistive magnets, they can go up to 30 Tesla, 35 Tesla. And they're huge objects, yeah, with a huge power consumption, yeah. But that's the utmost you can do in terms of a homogeneous magnetic field. If you go to long or short pulsed, microsecond, millisecond pulses of magnetic fields, then you can do even more. You can go to 20 Tesla to, say, 500 Tesla. And if you go to even higher ones, these are destructive experiments, as they are done in Los Alamos. Then you can go to, so these are experiments where the device destroys itself, yeah? But before it destroys itself, in view of an implosion or explosion, it sends a signal out, which is the measurement process. So it's a one-way experiment. So that would go up to 1,000 Tesla, yeah? But you see here with the pulses, you get already to very large fields. Now this is predominantly a material science issue over here. There's very little emphasis on atomic, if at all, on atomic physics from that kind of experiments. But there are even stronger fields. Not on Earth, not in laboratories, but for example in the photospheres of magnetic white dwarfs, which are typically a few kilometers, atmosphere of these objects, they go up to 100,000 of Tesla. And for 100,000 Tesla, the ground state of the hydrogen atom is already severely influenced. It's completely distorted by the magnetic field. But that's not the end of the story. If you go to very intense laser fields, for example, the magnetic component of these laser fields go up to 10 to the 6 Tesla. And then if you go to even more exotic astrophysical objects like neutron stars, you end up with 10 to the 9 Tesla. 10 to the 9 Tesla, the ground state of the hydrogen atom, the magnetic forces are 1,000 times larger, 10,000 times larger than the Coulomb force. Now, if you go to magnetars, you have spontaneous creation out of the magnetic field of E plus E minus. So you have all sorts of exotic objects at the very end of very large magnetic fields. Now, just for completeness, for electric fields, if you think about static electric fields, what you can have is something like 10 megawatt per meter in the laboratory. But if you go to laser fields, time-dependent electric fields, that can go up to something like 10 to the 15 volts per meter, which was, of course, if you think about an atom, would immediately ionize such systems. Yeah? And the intensity can go up to 10 to the 22 watts per square meter. So in view of all of that whole scale, yeah, you're going to be covering what does the term strong field really mean? Is it that n, or is it already here? So what does it mean? Yeah? And in order to elucidate that a little bit, let's take one concrete, I'm a theoretician, so let's take one concrete Hamiltonian and look at the terms. Yeah? So what I've written down here is the Hamiltonian for the hydrogen atom. And it has terms in it which you all know very well. It has the zero field kinetic energy, the p squared over 2m. It has the Coulomb rejection, which is responsible for the formation of the hydrogen atom. And it has a Zeeman term in it and a diamagnetic term. Now, in most cases in lectures, this diamagnetic term is usually crossed away. It says, well, B is small, we can neglect that, and we have a Zeeman splitting. But not so over here. We are interested in the situation that the diamagnetic term is indeed important. And what you can see already here, that it is of a very much different character as compared to the Coulomb interaction. The Coulomb interaction is a 1 over square root of x squared plus y squared plus z squared. So that involves all three Cartesian coordinates. But then the diamagnetic term is an oscillator type term, but it's an oscillator not in R, it's an oscillator in x and y, totally perpendicular to the magnetic field. So that is why this problem is a non-separable problem, and more than 1 degree, 2 degrees of freedom, and this is therefore a non-separable, nonlinear problem, and that is a necessary condition for a system on the classical side to become chaotic. Yeah? Now let's turn back to this kind of what is a strong magnetic field? Well, what you have to think about is you have to compare the energy with the diamagnetism. And so the diamagnetic energy, you want to compare it not to the absolute Coulomb energy, but to compare it to the spacing between two levels, Rydberg levels. In hydrogen, this spacing goes with 1 over n to the third, yeah? So that just is the difference between 1 over n squared minus 1 over n plus 1 squared, yeah? So that is 1 over n squared minus 1 over n plus 1 squared. And this goes roughly with 1 over n to the 3 if n is much larger than 1. Now,
black or
yeah, maybe better. Black one over here. So this is the 1 over n to the 3, which is responsible for the spacing between the levels. Yeah, you go up, and the level spacing becomes denser and denser. Now, what you have to compare in order to say is a magnetic field strong or not is this diamagnetic energy, which goes with n squared, yeah, and this spacing, which goes with 1 over n to the third. And this then altogether goes with b squared n to the 7th. Now that tells you a lot already. It just says, well, give me a b, and then I can tell you an n from which on this becomes larger than 1, and this becomes larger than 1 means that the diamagnetic energy is strong or is relevant compared to the spacing. And then I have a strong magnetic field. So it's not an absolute scale which is relevant. It is depending on the degree of excitation. A magnetic field of a certain strength will definitely from some end on become a strong field. And then you're in the non-perturbative regime, and all these beautiful non-perturbative phenomena will give rise to a structural complexity. Structural complexity you can see over here already. This is back to the work of Harald Friedrich and Peter Windken in the 80s and 90s. You see here the spectrum, part of the spectrum as a function of the magnetic field. Now this is the b-axis, the magnetic field in terms of Tesla. Sorry, these are very small labels. This is 1, 2, 3, 4, 5 Tesla. And here you see for very low fields these kind of bundles over here which correspond to the degenerate n-manifolds. First they split linearly with the B magnetic field, which is the normal Zeeman effect. This is happening all down here, yeah? But then you see after that linear splitting, things get really crazy. Yeah? You have a lot of avoiding crossings, and it's a really complicated spectrum. That's complexity in this spectrum. I have an enormously high level density, first in the degenerate manifolds, isolated with gaps, and then everything mixes and becomes, in this sense, really complex. So, so complexity is obvious. This is hydrogen atom Rydberg system in a magnetic field, but that appeals to a large number of systems, not just to this kind of Rydberg atom, like hydrogen or whatever. It appeals to all kinds of highly excited systems, atoms smaller than Laborarium, or weakly bound systems also in particular, where the magnetic field scale can become comparable to the relevant energy scale in the system, threshold phenomena, or new systems and processes that do not exist in the presence without the magnetic field and are induced exclusively due to the presence of the magnetic field. In astrophysical context, in cosmic magnetized objects, as I try to indicate, already the ground states are strongly influenced by these really strong magnetic fields in the sense of 100,000 of Tesla. So yeah, the field is in a kind of a knob which you can turn in order to influence and shape the system. Clearly, if you have a strong sensitivity on the field here, if you change a little bit, you really rearrange the spectrum completely. If you do a fine-tuning, then you can control the system. But controlling, in another sense, and if you're here in this spaghetti, control might not seem something you are offered by the system. Maybe it looks a little more friendly over here, but that depends really on what you want to be doing. Okay, so let's go to Rydberg after this introduction to Rydberg atoms in magnetic fields. So let's focus on the hydrogen atom. Of course, the working horse in most ultra-cold experiments are rubidium or other alkali atoms. Then you would have not just a proton, but you would have a tightly bound core from which your electron, which is highly excited, scatters off. This would introduce some modifications, sometimes important modifications, but most of the physics I'm going to be discussing here just equally hold for that case. I assume an infinitely heavy nucleus. Now in a magnetic field, that is non-trivial. I guess you're used to that if you have no magnetic field, then the center of mass motion separates from the electronic motion, meaning the motion of the electron with respect to the nucleus. Now that's true, of course, but not in a magnetic field. So the assumption of infinitely heavy nucleus is a more severe one in the presence of magnetic fields. Then you have this natural energy scale, and you equalize energy scales and see what happens. Now we have this Hamiltonian. We just had it again. So we have the Zeeman term, we have the diamagnetic, and we have the Coulomb direction. And now this is a slide which just tells you, from the 80s and 90s, the hydrogen atom in a magnetic field, which is here in the center of this slide, what has it been impacting? So there are several boxes here where the hydrogen atom in a magnetic field has been playing a crucial role, has been a paradigm for advancing this physics. This means magnetic cosmic objects. This is magnetic wide-bar physics. Many of the atmospheres contain hydrogen, and they contain then hydrogen in strong magnetic fields. So if you want to identify the chemical decomposition and properties of such an atmosphere, you need to know about hydrogen in low excited states, low lying excited states in such strong fields. The other issue is, and that's what I'm going to be addressing over here, high resolution laser spectroscopy, which was already available in the 80s, 90s. There people have, in strong fields, going through the levels and understanding what's happening in these very complex rearrangements of the levels. Then threshold phenomena. That means if your atom gets close to ionization, there are some particular phenomena at the ionization threshold, like the Quasi-Landau resonances, in these what people call magnetically dressed states. Yeah? And we will talk a little bit about that too, about this specific cooperative phenomena. Then the hydrogen atom in the strong magnetic field has also been a working horse for developing modern semi-classical physics of non-integrable systems. And that refers to the theory of unstable periodic orbits. Now that sounds a little strange because usually periodic motion, as you're used to from the pendulum, is a stable motion. But when chaos takes over, it turns out that unstable periodic orbits are particularly important. That means you have periodic orbits, but if you're close to them, you will depart from them because they are unstable then. So that unstable periodic orbits define the semi-classical physics of non-integrable systems. And then, of course, these interpolated nonlinear dynamics, mixed, rational, chaotic, phase space, quantum chaos. So that altogether was developments of roughly 20 years while people have been putting all these things together. Now, I think you had already Rydberg atoms in general, so I don't need to go through this in detail. We all know that Rydberg atoms are extremely sensitive and fragile objects, and with the principal quantum number n, their properties scale accordingly. So that means binding energy goes with 1 over n squared. The energy between the levels, we had that over here is 1 over n to the third. We have a radius of the object which scales with n squared. We have dipole moments, huge dipole moments with n squared. Polarizabilities with n to the 7. And all of these things are nowadays used extensively in ultra-cold physics to have long-range interactions between Rydberg atoms. And one big advantage also, radiative lifetimes go with n to the third, so you don't have nanosecond lifetimes like for low-lying excited states. You can go up to microseconds or even milliseconds if you put also, if you go either with n to very large in the hundreds, or if you go to the angular momenta of the states to very large values. So let me start with the hydrogen atom to try to explain a little bit what's happening if you increase the magnetic field and say we consider now a certain degree of excitation of the atom. We go into the semi-classical regime where semi-classical physics works, where there is a close link between classical physics and quantum physics. And so let's first have a look what happens on the root if we increase V. Remember from your lectures, we have the rotational symmetry of the hydrogen atom. And this is the special orthogonal transformations in 3 dimensions. And the generator of this rotational symmetry group of the hydrogen atom is the angular momenta. The angular momenta are the generators and which are conserved and are the generators for this symmetry. They are conserved quantities. Okay, this is one symmetry, which is the spatial symmetry in the system, which is obvious from the Hamiltonian because it's invariant under rotations. Now, there's a little more for that. And there's more even at zero field. There's the so-called Runge-Lenz vector. Yeah. This is a quantity which is nonlinear and a combination of angular momentum and momentum. So P, vector product L, and then a nonlinear part which goes with the unit vector along the radial direction. This quantity is again a conserved quantity for the hydrogen atom. It is a conserved quantity specifically for the hydrogen atom, not in general. Yeah? And it has a concrete meaning. As you know, in hydrogen atom, you have the conservation, you have the degeneracy, the quantum hydrogen atom, you have the degeneracy of the levels, not only with respect to angular momentum L, but also with angular momentum M, which is the magnetic quantum number, but also with respect to L. Now, the degeneracy with respect to L is due to the presence of these constants of motion. So there is something what people call supersymmetry. There's not only the rotational symmetry in 3 dimensions, there's also a supersymmetry due to this extra conserved quantity, and that here people call special orthogonal transformations in 4 dimensions. It's a super integrable system because there are more constants of motion than degrees of freedom. Remember from your classical mechanics lecture, an integrable system is a system that has as many independent constants of motion as it has degrees of freedom. Here we have more. That's why you call it super integrable. Now, what happens to this system if you turn on the magnetic field, V non-zero? Then it is a non-integrable system. Well, if you look back for a second, in this Hamiltonian, which has 3 degrees of freedom, x, y, z, the omega Lz is a conserved quantity. The Lz is a conserved quantity. The angular momentum around the homogeneous magnetic field is conserved. And the coordinate which is connected to that is the phi coordinate, the angle around the magnetic field axis. And these rotations are true symmetries if you rotate around the magnetic field axis. And that means this system has truly 2 degrees of freedom which are non-trivial. Yeah, that is, if you go to cylindrical coordinates, it would be rho, the distance from the magnetic field axis, and z, the coordinate along the magnetic field axis. So this is Lz is conserved, and then you have the rho and the z, the 2 degrees of freedom which are non-trivial. Now, what does it mean to increase the magnetic field? Well, if you want to get a picture of the phase space of the system, of the classical phase space, what you do is typically you look at a Poincaré surface of section. What is a Poincaré surface of section? Well, you have the phase space, and the phase space, say, has some sort of a shape somewhere here. Yeah? This is what people call the energy shell. This is all the possible configurations, energy as a function of x, p, x, y, p, y, z, p, z. Now in our case, it would only depend on rho and p rho, on z and p z, if I fix Lz, the angular momentum. Now, that would be the energy shell. And then what I do is, in order to get a representative picture of the dynamics, I do make in this is now a 2 degrees of freedom, but a 4-dimensional phase space. Yeah? And since energy is conserved, the manifold, the energy shell, is 4 minus 1, which is 3-dimensional energy shell. Now, if I take this 3-dimensional energy shell, I can hardly visualize anything 3-dimensional. What I want to do is do 2-dimensional pictures, because that I can nicely illustrate. So what I do is I make a kind of an intersection. Yeah? So at every time when the trajectory comes and hits this intersection, which for example can be defined by, for example, v rho equal to 0. Yeah, one of the velocities equal to 0. Every time one of the velocities, this velocity gets 0 in a certain trajectory, I report this intersection point. Yeah. So when all the trajectories somehow intersect through this intersection, and I report all these points. Now, what is the characteristics of such a Poincaré surface of section there, which is written here? Yeah? The main point is the following. Imagine you have a periodic orbit. A periodic orbit would give you a trivial signature over here. Yeah? Say it would be periodic, like this. It would hit here at a single point. So it would give you what people call a fixed point. Yeah? If a trajectory is more complicated, say it would be periodic in a more complicated way, it would give you a finite set of points. If you get in this intersection, now let's draw this intersection over here separately again, graphs like this, now this is lying in the plane of the intersection, then this means that your system is, all these intersection points are on such a closed curve. This is what people call quasi-periodic motion. So that is not periodic, it does not close, but it is quasi-periodic motion. Additionally, if you have structures like an arbitrarily seeming scattering of points here, then this is chaotic motion. So the Poincaré surface of section is a nice tool to visualize the type of motion which you have in phase space. Now there's a lot of understanding from nonlinear dynamics and chaos theory how a transition happens from a system that is regular, from a system that has periodic simple motion, to a system that has chaotic motion. Like in the hydrogen atom, in a zero field it is only periodic motion. In the presence of a magnetic field, as you shall see in a minute, it becomes chaotic. Yeah? So we have a very deep understanding how, with changing parameter value, this transition takes indeed place from a regular to a chaotic system. So this goes through quasi-periodic and then chaotic motion. Now let's look at this. This is a picture from the physics reports of Harald Friedrich back in 1989, which shows how the classical phase space changes with increasing magnetic field or increasing excitation energy for the hydrogen atom. If you go to very low fields, you see essentially these closed curves which I was mentioning earlier. So that means the dynamics of the electron around the nucleus is quasi-periodic. Yeah? It's almost periodic, it does not really periodic, but it almost closes and then goes back and forward in a very regular, repetitive manner. But then if you increase the magnetic field, you see that there are layers, what people call layers of stochasticity. And these layers come from these boundaries here and spread more and more with increasing field. And finally, you have a complete takeover of chaos for sufficiently strong magnetic fields or sufficiently high excitations. So your system indeed gets completely chaotic. There's some detail here which I don't want to emphasize too much, but there is a debate whether indeed Hamiltonian systems can become fully chaotic or not, which is not really proven whether they can or not. Truly speaking, there is tiny, tiny regular islands. You call these structures regular islands. Tiny, tiny regular islands in this, what people call chaotic sea. Yeah? So what you see there is, in terms of complexity, a very significant crossover from this regular periodic behavior to this chaotic behavior. Now, this is what classical physics offers to you if you look at the hydrogen atom. So, what about quantum physics? How would you tackle this problem in the case of quantum physics? Yeah. Before I go into the more description of what happens indeed in this crossover, let's just address this question. You would have to calculate all these thousands of excited Rydberg states, yeah? That is computationally very expensive. But most of the approaches which people have been and would use are based on variational principles. You have a basis set which you use, and that basis set has to be chosen carefully. Yeah? You don't choose something like, for example, if you choose the hydrogenic eigenfunctions for zero magnetic field, for the case to do the calculations in the presence of a magnetic field, you will fail from some point on, because this is not efficient enough to describe these highly excited states. But generally, basis set methods are, I think, or grid methods are the choice here in order to describe these highly excited systems. Of course, the calculations are then very expensive. What you have to do is you present the Hamiltonian matrix with these bases, and you have to diagonalize this matrix, so you end up with an eigenvalue problem. But since these are typically sparse matrices, you can use very efficient algorithms which are available since decades in order to diagonalize this system and get the eigenfunctions and get the eigenvalues. Okay, so let's turn back one step. I have been putting this in between. Let's go back to that one. Let's try to understand a little more how that crossover goes from here to here. If you look into the spectrum, this mess, this spaghetti mess I've shown you before, and people have been doing this, what you realize is that these avoided crossings of energy levels as a function of the magnetic field changes qualitatively if you go from weak to strong fields. At the beginning, you realize, if you look into the spectrum, that they are very narrow avoided crossings. Yeah? That means if you have typically the situation where magnetic field changes and you have some energy levels E, and they come close and they have an avoided crossing, then this avoided crossing for low fields is typically extremely narrow. Might be even difficult to resolve it. So this narrowness can be linked to the fact that for weak magnetic fields, there is still some approximate constants of motion. Yeah? So if you turn on the magnetic field, not everything lost is immediately. You see that here, not everything is lost immediately, but gradually chaos takes over, and this is reflected in approximate constants of motion. Yeah? You see here, this sigma, which has been discovered at the end of the 80s, is a combination of the Romme-Lenz vector components, and it turns out that it is a constant of motion approximately up to a certain order of the magnetic field. Now the gamma is the magnetic field in scale units. Yeah? So up to b squared, this is a constant of motion, and that makes for approximate separability, and that makes for these very narrow avoided crossings for weak fields. Yeah? In the strong, and then if you increase the magnetic field, what you see is that the states before that had definite angular momentum in the zero field case start to mix with each other. Yeah? And then if you increase even further, then even these states overlap that come from different n manifolds, that come from different principal quantum numbers. That makes for the complexity of the system, yeah? That makes it here. First here, you have this approximate constant of motion. Then you have here, say, the mixing of the different angular momentum states. And then out here, you have the overlapping of the different n manifolds. And there's no constant of motion, even approximately, left over in the system. Okay, so this is a picture, to my opinion, an impressive picture. I apologize for the low quality of it. When you compare experiment and theory. Now this is, originally the experiment was done in Weldes group in Bielefeld, back in Germany, and that shows here now, here the experimental data, and here the theory. All the sticks over here indicate individual states which have been calculated here. This is a window around the principal quantum number of n equal to 40. And you see, if you look in detail into it, it's amazing how well the agreement is between all these individual states and the ones that have been detected experimentally. So there's an excellent agreement between theory experiment on these highly excited Rydberg atoms in homogeneous magnetic fields. Thousands and thousands of states have been probed back in the 80s with this excellent agreement. Okay, now I've been showing you that there is classically a crossover between the regular behavior, between periodic and quasi-periodic motion, and the chaotic behavior. Now, how does that reflect itself in the case of the real quantum system, of the quantized Rydberg atom? Yeah? Now, this is the question I'm posing is, what is the signatures of chaos in the quantum system? Classically, we know what chaos is. It means you have this irregular behavior here, or speaking a little more quantitatively, you have this exponential sensitivity